Okay, we'll answer the questions one by one, and then I'm going to motivate a formula. The formula is called linearization of the function at a number. And then we're going to use the formula to approximate some values. So you just follow me. Okay? I will tell you everything. In item number 1, we are trying to write the equation of the tangent line to the graph of the function at the point where x value is a. Okay, I think we can just look at the graph in here. The condition is that the function is differentiable, of course, at any number. At least the function is differentiable at point a. I did not mention that, but when talking about tangent line, we mean the function is differentiable. We're trying to get the equation of the tangent line, to the graph of the function at this point. Now let's recall, in order to get the equation of the tangent line, we need two things. We need the coordinates of the point, right? And we need the slope. Okay. This point, so now let's say has. Give me a little moment. I'm going to change the color to something different. I cannot write white on white. You look at the mouse cursor. I'm talking about this point. This point has x coordinate of a, of course, and then the function has the equation of y equals f of x. So this point has x coordinate of a and y coordinate f of a. I'm going to write it down. Okay. This point has x coordinate of a and the y coordinate of f of a, right? We talk about the equation of the tangent line for the general case, for the general function f of x. Okay. And in order to get the equation of the tangent line, we need one other number. The other number is the slope of the tangent line. Okay, the slope of the tangent line is given. We have seen that many times. It's given by the derivative of the function f of x when x value is a. Okay. I'm going to write it down. Okay. For item number 1, I will squeeze it here. Can you see red on black? I think I can read. Okay, I will switch back to white. For item number 1, we have a point. The point is the point with the x coordinate of a and the y coordinate, so f of a, right? And the slope is given by, we have seen that many times, it's given by the derivative of the function at a. So we have seen that many times, right? In question 1, we are looking for the equation of the tangent line to the graph of the function at the point where x value is a. So the equation of the tangent line is, now recall the formula, okay? It's y minus y coordinate of the point, so which is the value of the function at a, and then equals the point slope form, okay? The slope f prime of a, right? And then times x minus a, the point slope form. We have seen this too many times. Now the application is relevant to the equation of the tangent line. I told you in the future we would use the equation of the tangent line over and over again, so that's one of the places. Okay. Okay. So we're done question A, item number A. Okay. In item number B, we are looking for a new term, linearization of the function when x value is a. this is actually a function for which the graph of the function is a tangent line. Okay, I'm going to tell you the answer to question 2. You will see what's going on. Okay, by that we mean we are going to solve the equation of the tangent line for y. By that we mean we write y in terms of x. We'll do that in 2 steps. Okay, solve the equation for y. We have y equals, you move the underlined term to the other side of the equation, so you have f of a, right, and then plus f prime of a, the derivative of the function at a, okay, and then times x minus a. So that's the thing we got after solving the equation for y. Now you see the right hand side is actually a function of x. It's a linear function of x, right? F of a is a number, a is a number, the derivative of the function is also a number. The only variable on the right hand side is x. That's why I said on the right hand side you have a linear function of x. Okay. Now we're going to use a function notation to denote the linear function. The linear function is called L of x. It's called linearization of the function when x value is a. Okay. In item number 2, the answer L of x is equal to f of a, I mean the value of the function at a, and then plus the derivative of the function at a, and then times x minus a. Okay. This is the formula for the linearization of the function at a. So that's actually the main formula I want you to memorize. Okay. I'm going to box that. I want to repeat. The thing in the box is a linear function. The linear function is called linearization of the function at a when x value is a. Very shortly, when we do some more questions, you're going to see L of x is actually a linear function. Okay. The only variable or unknown is x. So any questions so far? The box thing is called linearization of the function at a. Okay. Intuitively, you can see it. Actually, the graph of the function is the blue curve, and the straight line. I don't know the color. Okay, I told you before I'm a little bit colorblind. The line is the graph of L of x, right? The linearization. You see what's going on here. Okay. Now, the good thing about the linearization, I'm trying to say what's going to be useful as a volume. What's going to be useful as a volume. Okay. We'll make the point over and over again when we do questions. Now suppose you're trying to compute the value of the function at b. You're trying to compute the value of the function at b. By that we mean you're trying to compute f of b. Okay. Try to see the mouse cursor. Okay. The value of the function at b is given by the y coordinate of this point. I believe you can see the mouse cursor. Okay. I want to repeat, the value of the function at b is given by the y coordinate of this point, right? So which is that height, f of b, right? But in many cases, the value of the function at b is hard to compute. However, if the value of the function at a is simple to compute, we can use the value of L of x at b to approximate the value of the function f at b. I'm trying to say when b is very close to a, we can use the value of the linear function at b to approximate the value of the function at b. This is going to be useful to approximate some numbers. Okay. You just remember when B is very close to A, now item number 3. Okay. When f of A is simple to compute, so something was wrong earlier. Again, I want to repeat. Okay, when the value of the function at A is simple to compute, and also when B is a number very close to A, and then we can use the value of the linear function at B to approximate the value of the function at B. I will make this point over and over again using some particular questions. Okay. Okay. Now let's go over one question using the formulas, and when we do question B, I'm going to make my point. Okay, showing you how to approximate some values of the functions. So any questions about this slide? Simple stuff. It's nothing but the equation of the tangent line. Okay. The thing I want you to memorize is the formula in the box. Is the formula for the linearization of the function. Okay. Of course, you need to do some questions to really know what's going on. Okay. Now question A. Okay. In question A, copy the formula first. By copying the formula, I mean in this particular case, A value is equal to 100. I'm trying to say you use A value of 100 to copy the formula. Okay. In this particular case, L of x equals, memorize the formula. I want you to memorize the formula. Okay. Your final could be close book too. Okay. L of x is equal to, copy the formula. Okay. The value of the function at 100, A value is 100, right? In general, you have the formula L of x equals f of A, and then plus f prime of A, and then times x minus A in brackets. In case you forget the formula, you can recover from the equation of the tangent line. We just mentioned why the formula is true, right? But by copying the formula, I mean you use A value of 100 to copy the formula. And then the term after that is the derivative of the function at 100. Okay. And then times x minus A value is 100. Wherever you see A in the general formula, you replace A with 100. This is the linearization of the function. Okay. So, but of course, we're going to compute at least two numbers. We need to compute two numbers. You look at mouse cursor, f of 100, and also the derivative of the function at 100. Okay, in order to get the linear function. Linearization is going to be a linear function. We're looking for the linear function. So that makes sense? Copy the formula first, and then you can identify what numbers you're looking for. Okay. You're looking for two numbers, right? The first number is simple, right? The first number, you just compute the value of the function at 100, which is square root of 100. In the question, you see the function is square root of x, right? You replace x with 100. So the first number, the underlined number, is going to be 10. Square root of 100 is 10. Okay. For this one, it's kind of a non-calculator question. Okay, it's kind of how the calculator is programmed. basically I'm trying to tell you it may not be actually the same, but after you do calculus 2, after you learn some serious stuff, that's actually how the calculators are programmed. But this is the idea, kind of the idea you're going to use later in the course. Okay, you imagine you do not have a calculator, or you just imagine your computer can just do 4 functions. Okay, addition, subtraction, multiplication, and division. If you can only do 4 functions to calculator how to approximate numbers like square root of 102, square root of 98, and so on. Okay. Again, in calculus 2, you are going to have a better way, way better way to approximate the numbers like square root of 102 and so on. Okay. That's actually how your calculator is programmed. But now it's only the idea. It's kind of that. Okay. Okay, so we got the first number we need. So later on in the linear function, the first term, the underlined term, is going to be replaced with 10. Okay. Now how can we get the derivative of the function at 100? So before we do that, we have to differentiate the function. Okay. Okay, the derivative of the function at is equal to the derivative of square root of x. You know how to differentiate that. I told you a formula to memorize, right? It's 1 over 2 square root of x. Now you know why I wanted you to memorize the formula. So because you are going to use the formulas like differentiating 1 over x, differentiating square root of x over and over again. Now here is another time you see it, right? Okay. So after differentiating the function, you are ready to get the second number. The second number is the derivative of the function at 100. To compute this number, you need to plug 100 into the derivative of the function. Okay. By that we mean you have 1 over 2 square root of 100. Square root of 100, you can do it mentally, or you do not have to use a calculator. Okay. So this is what I meant by the value of the function at a is simple to compute. So I'm going back to this. Look at item number 3. This is what I meant by the value of the function at a is simple to compute. The value of the function at 100 is simple to compute. The derivative of the function at 100 is simple to compute. Okay. This one is 1 over 20, right? Square root of 10 is, square root of 100 is 10, and then 2 times 10 is 20, so you have 1 over 20. After getting the underlined and the double underlined, the two numbers, after getting the two numbers, you need to specify the linear function L of x. So L of x is equal to the value of the function at 100 is 10. Okay, f of 100 is 10, right? And then plus 1 over 20, the derivative of the function at 100, right? And then times x minus 100. So do you see that's actually a linear function? Again, so do not forget the name. It's called linearization of the function at a value of 100, or you can say at x value of 100. So the same thing. Okay. Any questions about this? Write down question A. So later on, I'm going to give you a chance to try another question at least. Okay. And then item number B is showing you how to approximate some values. Okay. In this particular case, we're going to approximate square root of 102 and square root of 98. Okay. We move on to B. Okay. Okay, now look at item number 3 in general again. Okay, we have seen the meaning, the value of the function at a is simple to compute. In this particular case, the function is square root of x. The value of the function at a value of 100 is 10. It's simple to compute, right? And the other condition we can approximate is that b is a number very close to a. In this case, in this particular case, we treat 102 as a number very close to 100. So that makes sense. If x a value is 100, and then 102, you treat 102 as the value of b. 102 is a number very close to 100, right? So that under these conditions, we can use the value of the linear function at b to approximate the value of the function at b. By that we mean we can use the value of the linear function at 102 to approximate the value of the function f square root of x at 102. I will show you the meaning in more details. Okay. Okay, in question number B, I'm going to write more wording. Okay. So first of all, you connect square root of 102 to the function. You leave a blank line, so probably I'm going to add one more sentence. Okay. You make the connections between square root of 102. That's a number you want to compute. You want to approximate using 4 functions: addition, subtraction, multiplication, and division. Okay. And then you connect that to the function f. What I meant is this is actually the value of the function f at 102. So do you see that's the value of the function at 102? I mean 102. You look at it backward. Okay, the value of the function at 102. The function is square root of x. It's square root of 102, right? I mentioned earlier, you treat 102 as a number very close to 100. 102 is your b, a is your 100. 102 is very close to 100. So that makes sense? 102 is very close to 100. I'm going to add one more sentence here. Now since 102 is close to, is very close. So can I say very close? Try to use our common sense to understand the meaning of close. Okay, 102 is very close to 100. Okay, so the value of the function at 102 can be approximated by the value of the linear function L of x at 102. So do you see it here? In general, when b is very close to a, then the value of the function at b at 102 is can be approximated by the value of L of x at 102. Right. Again, you imagine you put away your calculator, or you have only a 4 function calculator. Okay. Now we can approximate square root of 102. So what is the value of the linear function at 102? The linearization, I'm going to box that, is here. Okay. Now the value of the linear function at 102, all we need is to plug 102 into the linear function. So you have 10 and then plus 1 over 20, right? And then times, you're going to see this number can be computed without taking the square root, only using the 4 functions. Okay. By 4 functions, again, I mean addition, subtraction, multiplication, division. Okay. So do you see you have 102 in here, minus 100? Right. Again, the value of the linear function at 102, all we need is wherever you see x, you replace x with 102. Okay. So do you see you have 10.1? 10 plus 2 over 20, right? 2 over 20, you just have 10.1. Okay. Without taking square root, I believe you are going to have a very good approximation of square root of 102. I will convince you that you could convince yourself. So get your calculator, please. Now let's try to compute using your calculator. Okay, square root of 102. So do you see you have 10.0995, right? Which is very, very close to 10.1. Right? At this point, you can imagine it's not actually the case. You can imagine that's how your calculator is programmed. Okay, your calculator cannot get the actual value of square root of 102, but whatever number you see on your calculator is approximated value. Okay, so that's how you could program the calculator. So that makes sense. Again, in calculus 2, after we do series, I can tell you how your calculator is actually programmed. Okay. In old days, it's kind of useful, but nowadays, in some sense, it may not be super useful. But yeah, you have calculators, you have many other computer tools to calculate many things, right? But you just imagine that's how the calculator is programmed. Okay, so we're done one of the questions in B. Okay, I believe you see the other question is very similar. Okay, so the other question, square root of 98, we're going to approximate that. So you're probably on next screen. Okay, I mean on next slide. Very quickly, the same idea. Okay, square root of 98, you convert that, you connect that number to the function. It's actually the value of the function, at 98. Okay, and so because 98 is a number very close to 100 as well, right? Because 98 is very close to 100. So we can use the value of the linear function at 98 to approximate the value of the function f at 98. Now you plug 98 into the linear function. Okay, the linear function we're going to get. You are going to get, I forgot the formula already. Okay, I think it's 10 plus 1 over 20. You check your notes. Okay, I think 1 over 20, and then x value is 98, right? Minus 100 is equal to 10 plus 1 over 20. 98 minus 100. I think you have negative 2, right? So do you have 9.9? 9.9, okay. Again, if you use a calculator to calculate square root of 98, it's approximately 9.9. It should be very, very close to 9.9, okay. Any questions about this? Yeah, in any case, for all the functions, for all the questions, in step A, you'll find the linear function, linearization of the function at a number using the formula. Copy the formula first, okay? And then in most cases, actually in all the cases, you have two numbers to figure out. One number is the value of the function at a, the other number is the derivative of the function at a. In most cases, if to find the double underlined number, you have to differentiate the function and then you plug in the number, okay? And then you have a linear function, okay? After getting L of x, and then you can use the answer to that to approximate some values. Okay. If you don't have any questions, we'll move on to the next question. Okay. Most likely on the final exam, you are going to see a question very similar to question number 2. We'll do that in class. I will give you a chance to try after the class. I mean, I will give you assignment question to try. So very similar to that, okay? And then you should be ready for the question on the final. I know for you guys it's pretty far away from the final, but for all other people that are doing the final right now, so I always have final in mind at this time. So how about for question number 2? We do the following. It's almost time for a little break. I will give you 10 minutes. After you come back, probably you need 5 minutes to do question number 2a. After you come back, after you are back in 10 minutes, try to figure out as much as possible of this question. At least try to get the answer to question A, okay? To 2a, I mean. Okay. I will give you enough hint, okay? To get 2a, all we need is to differentiate the function, and then we plug in the numbers, right? To differentiate the function, the derivative of the function is actually you are trying to compute the derivative of, so now let's say, so 6th root of x, right? For any radical, you'd better convert the function to a power function before you can use the power rule. I think we have seen this many times. Inside the brackets, convert the function to the form of a power function as x to the power of 1 over 6, right? You differentiate that. Now you know how to use the power rule, right? So this one you know how to use the power rule. So this one is a 1 over 6. It's kind of the derivative of x to the power of n is equal to n times x to the power of n minus 1. 1 over 6 minus 1, you have negative 5 over 6, right? But later on, you need to plug in some numbers to evaluate the derivative. I'm trying to say, in order, it's easier to evaluate the function as some numbers, you'd better convert the function to the form of a radical form, convert back to radical form, so that it's easier to see the value of the function. Okay. So this one, I believe, is you have 1 on top, and then you have 6 on denominator, and then you have 6th root of x to the power of 5, essentially the same thing. I'm trying to say the derivative after differentiating the function, in order it's easier to evaluate the derivative at some number, at any number, you'd better use the radical form. You know how to convert from that step to that step, right? For question A, I still want you to copy the formula first. Okay, copy the formula. The function you're looking for is given by use a value of 64. Okay, the value of the function at a 64 at 64. I mean, okay, and then plus the derivative of the function at a and then times x minus a. Copy the formula first, so you know what you are looking for. Right? You are looking for the value of the function at 64. You are looking for this number, right? You are also looking for the derivative of the function at 64. Okay. After differentiating the function, it's easy to figure out the two values. So the value of the function at 64, you can do this mentally, right? It's 6th root of 64. To get this number, you do not need a calculator. Try not to do anything using a calculator. Try not. Okay. So because I think for the exam or the assignment, I'm going to specify I want you to write the final answer as a fraction. Any number written as a fraction can be manipulated using full function calculator, right? For this number, you just think which number to the power of 6 is equal to 64. I think you have 2, is that right? I think that's 2. Yeah, 2 is right, I think. And so we have found the underlying number. Okay. The double underlying number, I mean the derivative of the function at 64. We need to use the derivative of the function. Okay. Can I write this in one line so that it's easier to see what's going on? So we have seen that, right? The derivative of the function at 64, you plug a value of 64 into the function. I mean into the derivative. So you have 1 over 6 times 6th root of 64, and then the whole thing to the power of 5. So do you have 1 over 6 times 6th root of 64 is 2 to the power of 5. I think it's 32, is that right? And then I do not know the product. 1 over, so anybody want to tell me the number? 6 times 32? 6 times 32, please. I'm only using 4 functions, okay. Yeah, 192. So thank you. It's 1 over 192. Okay. Okay, so now we have all the numbers we need in order to get the linear function. So linearization, I mean. So we have the linearization of the function L of x is equal to 2 and then plus 1 over 192 and then times x minus a, x minus 64. So we're at question A, right? This thing is going to be used to approximate some values of the function. Okay. Actually, originally, if you want, the question is probably the following. Okay, you want to use something to approximate, let's say, 6th root of 65, and then you get a closer number, so that the 6th root is simple to compute. So you choose a value to be 64. And then you connect this to the function, and then you can use the value of the function at 64 to approximate the value of the function at 65. Okay. But in the future, most questions are going to be given in that format, so that you do not need to identify the function. You do not need to identify at what value it's simple to compute, and so on. Okay. Now we move on to question B. Okay. In question B, again, in question B, we are trying to approximate 6th root of 65. You connect that to the function. Okay, is the value of the function f of x at 65. I mean. I meant 5 in here, sorry. So because we can treat 65 as a number very close to 64. Okay. So the value of the function at 65 can be approximated using the value of the linear function at 65. So which is you plug 65 into the linear function. You have 2 plus, I think you have 1 over 192, right? And then times 65 minus 64. This number, again, in the future, I want you to write everything in terms of a fraction. For question B, for question 2B, or the similar questions, in many cases, I want you to write the answer using a fraction so that you can see it can be computed using full function calculator. Okay. Can be manipulated by the computers. Trust me, computers can only manipulate full functions. I don't know this number in fraction form. This number in fraction form, I think is 192 times 2. Uh, 385 over 192. 385. Probably that's right. Again, for the assignment or on the final, I'm going to specify write the final answer as a fraction. Okay. And likewise, 6 root of 63, the same story, right? Is equal to the value of the function at 63. Can be approximated by the value of the linear function at 63. So which is 2 plus 1 over 192, and then times 63 minus 64. I think I can guess the final answer. The final answer should be 192 on denominator. So do you have 383 on numerator? Okay, that's how we do question number 2. If you use a calculator to convert 6 root of 65 and the right hand side, the fraction, I believe you are going to see the two numbers are very close, very close. Again, at this point, I want you to imagine that's how your calculator is programmed. In calculus 2, we're going to see way better method. Write down question 2. So any questions about this? 2 should be simple, right? Okay, now let's move on to 3. 3 is a little bit weird, a little bit complicated. Okay. We mentioned before in calculus we never use degree measurement, but so this time I'm trying to say you have to convert the degree measurements to radians. If you know what to do, then you do not have to listen to me. You can keep on trying. If you want to listen to me, I'm going to go over the solutions. So probably I will give you a chance to try. And by the way, for all the applications, for all the topics regarding applications, the questions are kind of long. I cannot do something like I give you time to do the entire question. But still, I will try to give you as many chances as possible to practice. Okay. Now we work on 3A first. Okay. In any case, copy the formula so that you know what you are going to get. The formula is going to be the following: a value is pi over 4. Okay, the value of the function at a, value of the function at pi over 4, and then plus the derivative of the function at pi over 4, and then times x minus a, x minus pi over 4. Right. This time the answer could be, I might ask you to write the final answer in terms of pi, okay? Because you know approximate value of pi 3.14 something, right? In any case, we're going to figure out the two unknown numbers, the two numbers. After we got the two numbers, we can get a linear function, right? In order to get the two numbers, so maybe I'm going to copy the function. The function is tan of x, right? Later on, we're going to get the value of the function at pi over 4, and then the derivative of the function. You know, we also have to differentiate the function, right? That's why we call the topic applications topic. Okay. The derivative of the function is equal to the derivative of tan secant squared of x. Okay. And then in order to get the linear function, we need the value of the function at pi over 4. We need the derivative of the function at pi over 4. Okay. The value of the function at pi over 4, I mean tan of pi over 4 unit circle. Anybody want to tell me tan of pi over 4, please? Look at the unit circle, okay? Probably I have some assignments here. The unit circle thing is on any assignment. Look at the unit circle in here. Look at the angle pi over 4, 45 degrees. Tan is computed using y over x. This point on the unit circle has x coordinate and y coordinate, the same number, right? So tan of pi over 4 is equal to 1. Okay. Whenever you are trying to get the trig values of special angles, I mean the angles like the multiples of pi over 4, multiples of pi over 6, multiples of pi over 3. These are the special angles. For the trig values of the special angles, you'd better use the unit circle, or better if you can memorize the commonly used values. So yeah, that better. So this number is 1, right? Okay, we also need the derivative of the function at pi over 4. By that we mean we need the value of the derivative of at pi over 4. Okay, which means we need secant squared of pi over 4. Secant squared is hard. It's kind of hard to see. If you are used to it, it's okay. But I think for most people, you might want to convert the thing to 1 over cos of pi over 4, the whole thing squared. Okay. I mean, you know, secant is the reciprocal of cos, right? So I have 1 over, so something squared. You look at the unit circle again. The angle we need is also pi over 4, right? Cos of pi over 4 is given by the x coordinate of the point. Can you see the mouse cursor? The x coordinate of the point, which is square root of 2 over 2. Okay. Now all you need is to compute square root of 2 over 2, the whole thing squared. I'm going to run a little slower for this, okay? So do you see you have 1 over 2 over 4? This value is actually 2, right? I mean 1 over 2 over 4 is the same thing as 1 over 1/2. Okay, so the final answer is 2. That's the value of the derivative at pi over 4. Alright. Now we're ready to get the linear function. So the linear function, okay. So the linearization of the function is equal to 2. Sorry, it's 1. The value of the function at pi over 4 is 1. And then plus the derivative of the function at pi over 4, which is 2, right? And then times x minus pi over 4. I think question A is simple, right? You just follow the formula, evaluate the function at pi over 4, evaluate the derivative at pi over 4, and plug in the numbers. You can get the answer. Now let's move on to B. Okay. Again, in calculus, we rarely use degree measurements. In almost all the cases we use the radian measurements. Okay. But in question B, you see you're trying to approximate tan of 44 degrees and 46 degrees. Okay. So you need to convert the degrees to radians so that you can use the method in calculus. I'm trying to say in calculus, whenever you see tan of x, secant of x, whatever trig function of x, that x is radian. So how about we do we approximate tan of 46 first. So you like addition is better than subtraction, right? In any case, we're going to do some conversion first. Okay, we're going to convert the 46 degrees to radians. Okay, how can we do that? We just mentioned earlier how we convert from the degrees to radians. The only thing you need to remember is pi radians. For radians, you do not even have to write radians, but for degrees, you have to use a circle, right? Pi radians is equal to 180 degrees. That's the only formula you need to use. So 1 degree is equal to pi over 180 radian. So that makes sense. From that equation, you divide two sides of the equation by 180. On one side you have 1 degree, right? On the other side you have in radian, pi over 180. I mean 1 degree is the same thing as pi over 180 radians. We're going to use that to do the conversion. Okay. Actually, 45 degrees is equivalent to pi over 4 radian, right? Radians, I mean. Okay. So you'd better rewrite 46. I'm trying to say you'd better rewrite 46 degrees as 45 and then plus 1 degrees. Okay. It's equal to 45 degrees and then plus 1 degree, right? Why I want to do that, you're going to see it very shortly. Because it's easier to get the trig values for 45 degrees or pi over 4 radian. Now we're going to convert that to radian, to how many radians? Okay. 1 degree is equal to pi over 180 radians. You just multiply pi over 180. It's going to be converted to radians, right? I'm trying to show you the final answer is okay. So do you see the final answer is pi over 4 and then plus 1 over 180? That's how I want to make the connection. I'm trying to say 46 degrees is equal to pi over 4 and then plus 1 over 180 radians. If you do some simple calculation. So that's the point I'm trying to make. Okay. After this, we're ready to approximate. We're we're ready to approximate 10 of 46 degrees. Okay, so 10 of 46 degrees is equivalent to 10 of pi over 4 and then plus 1 over 180 radians, right? Now we connect that to the function. Okay, it's actually the value of the function. It's the value of the function. You know, you have to connect the value you want to approximate to the function. It's the value of the function at pi over 4 and then plus 1 over 180, right? At this point, you see this pi over 4 plus 1 over 180. So because 1 over 180 is a very tiny number, right? Of course, 1 over 180 is a tiny number. Okay, so this thing can be approximated by the value of the linear function at pi over 4 and then plus 1 over 180. I hope it's not too squeezed. So can I move to here to connect? Is equal to. Now all we need is to plug pi over 4 and then plus 1 over 180 into the linear function. Now you watch the linear function. Okay, the linear function is 1 plus 2. Now look at this line. 1 plus 2 times x value is pi over 4 and then plus 1 over 180 minus pi over 4. Amazingly, the final answer is not in terms of pi. So you have 1 plus 2 over 180. So you have 1 plus 1 over 90. I mean 1 over 90, not 98. 1 over 90. If I want you to write the answer in terms of a fraction, so the final answer I believe is going to be 91 over 90. Right. Okay. Now you can change your calculator to the degree mode. Probably you want to compute two numbers. You compute 10 of 46 degrees, and the other number you might want to compute is 91 over 90. I believe these two values are very close. Okay. If you want to approximate 10 of 44 degrees, I believe the idea is very similar. Okay. I'll see if I can modify something from here. Okay. To approximate 10 of 44 degrees, I believe the conversion is going to be something like the following: pi over 4 minus 1 over 180. And then all you need is to change all the signs to minus signs. Okay, tan 44 degrees is pi over 4 minus 1 over 180. It's the value of the function at pi over 4 minus 1 over 180. It can be approximated by the linear function at pi over 4 minus 1 over 180. Now you use the linear function, okay? Pi over 4 minus 1 over 180 minus pi over 4. Yeah, and then you have 1 minus 2 over 180. You have 1 minus 1 over 90. This number is 89 over 90. Okay. Again, if you want, you can try to use your calculator to compute two numbers, tan of 44 degrees, and the other number is 89 over 90. The two numbers are very close. Okay.